xy plane is sometimes called the complex plane. So any complex number can be representing a point on xy plane, and that point is x plus yi. X-axis is a real axis, and y-axis is imaginary axis because that's the coefficient of I. Here I is a square root of -1, imaginary unit. And now if this point in xy plane or the complex plane represent the complex numbers, then there is an absolute value of that complex number, which we've been writing as r, which is square root of x squared plus y squared. And now theta is always from positive x-axis to the line segment connecting the zero and the complex point, and that's the theta. And since it's forming a right triangle right here, x is always absolute value of the complex number times the cosine theta, because the absolute value of a complex number is serving as hypotenuse. And y is absolute value of complex number sine theta. Now, if you write it this way, instead of x plus y, yi, that's rectangular form of the complex number. But instead of writing the complex number in x plus yi rectangular form, if I rewrite that complex number, and so this one is a rectangular form, but instead of x, I write it absolute value of complex number times cosine theta replaces x, and then absolute value of complex number times the sine theta replaces y. And the second form right here is called the polar form or trig form. Now, since the absolute value of z is a common factor, I can take it out and I can write it as a cosine theta. So I'm going to put I in front of the sine theta to make sure I is not inside of sine function right here. And sometimes we write this as R C CIS theta, which notation your textbook might use. And I prefer this notation, R times e to the I theta, which means e to the I theta later will be proven is exactly the same as a cosine theta plus I sine theta. This is mathematically correct. So e to the I theta equals cosine theta plus I sine theta. Because if you write the complex number x plus yi, the rectangular form, to trig form, what identifies that complex number is r, the absolute value of the complex number, and the theta. Because of that, it's r times e to the I theta will be the trig form of the complex number. Let's actually go over one example where we're converting complex number to the polar form, which I've done that in previous video, but I want to do one more example. So here, this complex number is given to you as a rectangular form. So this complex number, 1 plus I minus I square root of 3, which means x equal 1 and y equal negative square root of 3. And that complex number is in fourth quadrant. And so that complex number is in fourth quadrant, x equal 1, y equal negative square root of 3. So this complex number is 1 minus I square root of 3. And now I need to know what's the absolute value of a complex number, which is r, which is the square root of x squared plus y squared. Now x squared, which is 1, and y squared, when you square the negative, it's positive. Square root of 3 to the square is just 3. And so that means it's a square root of 4. Of course, we're going to simplify that since the square root of 4 is equal to 2. So r, the distance from 0, 0 to the point, complex point, is the absolute value, distance of the complex number from 0, 0, which is given to you as a 2. So now I got r. Now I need to know the theta. So the best way to find the theta is you find the reference angle first. And the actual angle you're looking for is this angle. So reference angle 360 minus the reference angle, if you're doing it in the degree. If you are doing it in the radian, 2 pi minus the reference angle is the angle I'm looking for. And so how do you find the reference angle? So the reference angle is always tangent inverse of absolute value of y of x. So a reference angle is always positive acute. And y is square root of 3. Absolute value means I ignore the negative sign. So tangent inverse of square root of 3. Tangent inverse of square root of 3 is 60 degree or pi over 3 radian. So it's the same. Now that's reference angle. So the actual angle theta is either 2 pi minus the reference angle, or if you're degree mode, 360 minus 60 degree. So the theta itself will be 2 pi minus the reference angle, and 2 pi is 6 pi over 3, and minus reference angle. So you're talking about angle 5 pi over 3. And if you're doing it a degree, and theta is 360 minus the reference angle, and through 300 degree will be the theta in degree measure versus radian measure. And so the complex number that we just written is 1 minus I square root of 3 is the rectangular form. And if you convert it into polar form, R is 2 cosine theta 5 pi over 3, and that's x, and then I times y. Y is a complex number, absolute value, times sine and theta 5 pi over 3. That's a trig form. But since 2 is a common factor, if you factor it out, it can be written as cosine 5 pi over 3 plus I sine 5 pi over 3. Or simply the other notation, cis angle, or my notation, 2 times e to the I 5 pi over 3. If you're doing it a degree, it's 2 times e to the I 300 degree. Either works with me. So whether you write this one the long way, complete form, trigger form, this, you have to know that that is equal to this and that's equal to this. They are just either radian mode or the degree mode. Now, if I go opposite direction, meaning I give you a trigger form and you want to convert to rectangular form, which is more straightforward. And so this complex number is given to you in trigger form. Now, then this is the same as a 3 cosine 2 pi over 3 plus I sine 2 pi over 3. And of course, a 3 cosine 2 pi over 3 is your x. And then I 3 times a sine 2 pi over 3 is your y. And so when I convert into rectangular form, whether I multiply I over here, it's the same. So 3 times cosine 2 pi over 3. 2 pi over 3 is the second quadrant and cosine is negative. So you know it's a negative 1 over 2. And this is 3 times sine 2 pi over 3. 2 pi over 3 is the second quadrant, sine is positive. It's the same as sine pi over 3, sine 60 degree. So it's a square root 3 over 2. And now I just have to multiply 3. So negative 3 over 2 is your x. And 3 square root 3 over 2 is your y. And so x plus yi, this is your rectangular form. And so you can see 2 pi over 3 is in second quadrant, so x is negative, y is positive. So this one is your rectangular form. So rectangular form is straightforward. You have to just know how to compute cosine angle value and sine angle value. Now you went through how to multiply two complex numbers in algebra. Now if the two complex numbers are in polar form, how do I multiply? Is that you multiply R1 to R2, the absolute value of the complex number, times absolute value complex number, and e to the I theta. When it comes to theta 1 and theta 2, you don't multiply them, you just add them. Now this one can be proven by some identity of sine and cosine. So let me do the proof of this. And so if I multiply z1 times z2, and so z1 is equal to, if I write a complete form, it's r1 cosine theta 1 plus I R2, R1 sine theta 1. And now you're multiplying this times Z2. And now Z2 is R2 cosine theta 2 plus R2 sine theta 2 times I. And so if you multiply this times this, distributing right here, I have R1, R2 cosine theta 1 cosine theta 2. Now if I multiply this, and I have R1, R2 cosine theta 1 sine theta 2 I. Now if I multiply these two, I have R1, R2 sine theta 1 cosine theta 2 I. Now if I multiply these two, I have R1, R2 sine theta 1 and sine theta 2 times r to the square, I to the square. Now I to the square is equal to -1. So there's I times I to the square. I to the square is -1. So I to the square will be replaced by -1. We're going to put it in front of here. Here, I square got replaced by -1. Now let's combine the like terms. These two does not have I, so I can add these two, but as you can see, the common factor is R1 and R2. And then I write it cosine theta 1 cosine theta 2 minus sine theta 1 and sine theta 2. And that's nothing but the sum identity of cosine theta 1 plus theta 2. And now I'm combining these two that contains I. And so if I combine that, then I get I as a common factor, R1 and R2, product of R1 and R2 is a common factor. And I have cosine theta 1, sine theta 2, plus sine theta 1, cosine theta 2. Or you can write this one first and this one later, sine theta 1, cosine theta 2, plus cosine theta 1, sine theta 2. And that is a sum identity of sine theta 1 plus theta 2. So this gets replaced by R1, R2 cosine theta 1 plus theta 2, some identity of cosine. And then here R1, R2, this gets replaced by sine theta 1 plus theta 2. So as you can see, R1 times R2 will be the absolute value of the Z1 times Z2. And then I have a cosine theta 1 plus theta 2, sine theta 1 plus theta 2, and then I that. So this is going to be my x of the result. This is going to be my y of the result. So I can write it as a e to the I theta 1 plus theta 2. Hence the formula. And you can do the same thing for division of complex number. When it comes to division, you do the R1 divided by R2 and theta 1 minus theta 2. So I'm going to apply the formula to multiply and divide a complex number. So now I have a complex number in polar form. If you are to multiply Z1 and Z2, you multiply R1 times R2, which is 6, and then you add the angles I, 50 plus 30. And so add them together is 80. It's just 6 times e to the I, 80 degree. So when it comes to angle, you need to add. That's a multiplication. Now when it comes to division, z1 divided by z2 is I'm going to divide 2 over 3. And then you're going to subtract the angle theta 1 minus theta 2. And so 2/3 is the R as a division. And then I, 50 minus 30 is a 20 degree. So that's the division of complex numbers in polar form. Now, multiplying two complex numbers, and if you do not want to convert to polar form, but it is useful to use polar form when you're multiplying complex number to the power n is big. So any complex number in rectangular form to the power 8, if you imagine you multiply 8 times the same complex number, it's going to be tedious and long. But when you do the complex, when you multiply complex number to the power n using the Moivre theorem, it will be a lot simpler. So if you multiply complex number times itself, and you can imagine r times r, e to the I, theta plus theta, it's a 2 theta. So if you multiply, so that's just z to the square. If you can imagine z to the cube will be r to the cube with you add the same angle 3 times, like this. So and so on. So z to the n equals to r to the n e to the I n theta. So this formula is called the de Moivre theorem. It will be very useful when you're multiplying a complex number in rectangular form, complex as it is. So we'll convert it into polar form and then use this de Moivre theorem, and then we convert back to rectangular form. So let's do an example. Now we have a complex number -1 plus I to the 13. So you don't want to multiply -1 plus I to the 13 by hand, long and tedious. So I'm going to convert first negative, so the complex number -1 plus I, and this is in fact z to the 13. And we don't want to multiply as it is, so I'm going to convert that to rectangular form. Polar form, right? Rectangular form is given to you, so I want to convert this to polar form first. And so R is the absolute value of the complex number, which is square root of x squared plus y squared. And x equals -1. -1 to the square is +1, and y is 1. 1 to the square is 1, so absolute value of complex number is just square root of 2. Now you are in second quadrant. This complex number is in second quadrant because x is negative and y is a positive, and this point right here is -1 plus I. As you can see, and the absolute value of R, we've already found it, absolute value of complex number to be square root of 2. And then you can see the reference angle is a tangent inverse of absolute value of y over x, reference angle, and which is a tangent inverse of 1. Absolute value means ignore the negative sign. 1 over 1 is 1. Tangent inverse of 1 is pi over 4 in radian, or 45 degree in degree measure. The actual angle that you're looking for is 180 degree minus the reference angle, or pi minus the reference angle. So the angle you're looking for is in degree measure. It's 180 degree minus 45 degree, which is 135 degree. And so this complex number, -1 plus I in rectangular form, can be changed into square root of 2 times e to the I, angle 135 degree. Now that's not the end. We are looking for z to the 13. And so what is -1 plus I to the 13? Which is the same as a square root of 2 e to the I, theta 135 degree to the 13. Now, according to the de Moivre theorem, just square root of 2 to the 13, and then e to the I, 13 times 135 degree. And so square root to 2 to the 13 means square root to 2 to the 12 times square root to 2 to the 1. And then e to the I, what's 13 times 135? That's 1755 degree. And if you divide 1755 degree to 360, if you divide that 360, then you get 4.875. What it means is that it's a full complete turn plus 0.875 of 360 degree. So you subtract 4 and you multiply 0.875 by 360. So that's equal to coterminal to this one right here is 315 degree. So that means 1755 degree is a coterminal to 315 degree. Now square root to 2 to the 12 is 2 to the 6 because square root to 2 is 2 to the half. And so if I do the 12 right here, which is 2 to the 12 over 2, which is 2 to the 6, and square root to 2. And now 1755 is coterminal, and 2 to the 6 is 64, as square root to 2. And now what I have is 315 degrees. So I have cosine 315 degree plus I times 64 square root to 2 sine 315 degree. Because our goal is to go back to the rectangular form. Now 64 square root to 2 cosine 315 is same as cosine 45 degree, which is 1 over square root to 2. And plus I sine 64 square root to 2 sine 315 same as a negative sine 45 degree, which is a negative 1 over square root to 2. Now you notice that 1 over square root to 2 is the same as square root to 2 over 2. Check that by rationalizing it. And now what I have here is that square root to 2 and square root to 2 cancels out. And what's just left is 64. Now here the same, square root to 2 and square root to 2 cancels out, but there's a negative right here. So it's a negative 64i. So that's a final result. And this is in rectangular form, negative 1 plus I to the 13. So if you do it, convert it to polar and use the Moivre theorem, to the power exponential is simpler. Now we are going over nth root of a given complex number, especially if I want to get a fourth root of a given complex number. The first step is going to change the complex number to polar form r e to the I theta. So after that, the first complex fourth root of them will be fourth root of r times e to the I theta. You want to divide theta by 4, so that if you multiply 4 times, so theta over 4 times 4 becomes a theta. That's w1 to the 4 has to be equal to z. So once you find the w1 to the 4 equals to z, and once you find that w1, I'm going to show you how to do w2 and w2, 3 and 4. There are always nth root of complex numbers. So let me start with just an example, and I will explain why is that later. So now I'm going to convert first the given complex number to polar form. Now, given complex number is negative square root to 3 plus I. And now absolute value of z is r, which is a square root of x squared plus y squared. Now x squared, square root to 3 to the square, negative square is positive, square root to 3 to the square is plus 3, and 1 to the square is 1. And now that's a square root to 4 and simplified as a 2. So r equal 2, and e to the I theta. Theta, we're going to find the theta by theta prime first, reference angle. It's a tangent inverse of absolute value of y over x. Now, absolute value means ignoring negative, so y is 1 and x is square root of 3, which is tangent inverse of square root of 3 over 3. You know that's your 30 degree, and that's reference angle. But now this complex number right here is a negative x, positive y, you are in quadrant 2. So that complex number in the second quadrant, with the point with the x as a negative 3, negative square root of 3, and y as a 1. This complex number right here, and since the reference angle, since this one is a 30 degree, the angle you're looking for is 180 minus 30 degrees, so it's 150 degree. So I can say the theta itself is 150 degree. Now, so there are 4 fourth roots. So the first one you're going to get is w subscript 1. It's a fourth root of r, and r is 2. So fourth root of 2, and we're going to divide 150 degree by 4. If you divide 150 by 4, you know it's a 37.5 degree. 37.5 degree, which is 150 degree divided by 4. Theta, the theta divided by 4. That's the first root. So that means that this angle right here will be 37.5 degree. That's 150 degree divided by 4. And now r is 2. So fourth root of 2 is your radius of this one. So then all the fourth root of the complex number is sitting on the circle with the radius, so fourth root of 2, and they are equal angle apart. And so W1 is over here, which is fourth root of 2 times e to the I 37.5 degree. And the next one is equal angle apart. That means I can divide this one into exactly 4 equal angle, 90 degree apart. So the next root, fourth root, will be here. That's 90 degree more than 37.5 degree with the same radius r. So that's W2, that's W3, and that's W4. And they are 90 degree apart. So the fourth roots are all equal angle measure apart on the same circle, and that circle's radius is fourth root of 2. So then how to find the W2 is fourth root of 2 times, it's a 90 degree more than 37.5 degrees. So you will just have to add 90 to that. So it's 127.5 degree. And now W3 is a fourth root of 2 and then 90 degree more than 127.5, so it's 217 degree 0.5. And now W4 is a fourth root of 2 e to the I add 90 degree to that, that's 307.5 degree. Now you can easily verify either of this fourth root. So W1 to the 4 is the complex number, 2 times e to the I 150 degree. You can check that W2 to the power 4 is also 2 to the I 150 degree. There will be some angle to coterminal to that. And W3 to the power 4 is also that, 2 times e to the I 150 degree. W4 to the 4 equals 2 times e to the I 150 degree. And that's why W1, W2, W3, W4 are fourth root of complex number, since you can multiply this itself 4 times to get this number. Now, I'm not going to check all 4 of this. Let me check only this. I will check this, and you can check the rest. So I'm going to check this one. So imagine I have W4, which is fourth root of 2. So if I do the fourth root of 2 and W4 to the power 4, so W4 is fourth root of 2 times e to the I 307.5 degree. So that's W4. If I do the power 4, exponent 4, by the Moivre theorem, I need to do the fourth root of 2 to the power 4, which is equal to 2, e to the I, and you're going to multiply 4 times 307.5 degree. And of course, fourth root of 2 to the 4 is just 2, e to the I. 307.5 multiplied by 4, 307. 1230 degree. Now, if you divide 1230 by 360, and that's a 3 complete ton. So 3 times 360 plus 150. And so that means this one is simply coterminal to 210 degrees. So that's why W4 to the 4 is equal to 2 times e to the 150 degrees. So that's why W4 is the fourth root of this complex number. Since I checked the W4 to the power 4 equals the given complex number, you're welcome to check W1, W2, W3 to the power 4. Sometimes question may ask you to leave the complex fourth root as they are in polar form, or sometimes they may ask you to change it to rectangular form. If it is asking you to change it to rectangular form, you will have to give me an approximation of r times the cosine 37.5 degree as an x, and then fourth root of 2 times the sine 37.5 degrees your y, and you will have to approximate that using your calculator. And so that one is approximately, if I round it to 4 decimals, 0.94346 plus this one is 0.7239 0.72394 I, and that's an approximation. And you can do the same thing for W2 and W3 and W4 using your calculator. So since they are 90 degrees apart, X and Y get swapped. So make sure you are doing this one right here. It's a fourth root of 2 times cosine 127.5. This one right here is fourth root of 2 times sine 127.5. So same here. Fourth root of 2 times cosine 217.5. And this one right here is a fourth root of 2 times sine 217.5. And this right here is fourth root of 2 times cosine 307.5. This one right here with the negative inclusive is a fourth root of 2 times sine 307.5. This one is example 3 in my lecture note of the second part of the lecture note. And I'm going to modify the question to fifth root because I already did the fourth root. So I'm going to modify this as a fifth root. And so x to the 5 plus 1 equals 0. Solving this one in complex solutions, then we are looking for x to the 5 is equal to negative 1. What are x is? X is our fifth root of negative 1. Now, of course, negative 1 in complex trig form, polar form, is negative 1 means your point, complex point, is a negative x-axis. And since your complex point is negative 1 over here, so the angle theta is 180 degree. And of course, distance from 0, 0 to the complex number, which is absolute value of the complex number, is 1. So this can be written as a 1 times e to the I 180 degree in polar form. Of course, I don't have to write the one, but I'm going to write it because I have to get a fifth root of that. So solving the equation in complex numbers, x to the 5 plus 1 equals 0 means x to the 5 is equal to negative 1. What are x's? The solution x's are nothing but the fifth root of negative 1. So we are looking for fifth root of negative 1 complex solutions. Since this is the complex number, this is complex number whose fifth root you're looking for. So the fifth root are the x value, the solution value. So I'm going to get a fifth root of 1. And then e to the I said the first fifth root will be 180 divided by 5. 180 degree divided by 5. Fifth root of 1 is just 1. So 1 times e to the 180 divided by 5 is 36 degree, I believe. So this complex number, fifth root of negative 1, should be sitting on the radius of the fifth root of 1. Fifth root of 1 is just 1. So this radius of the circle is fifth root of 1, which is 1. So that's why it's unit circle. The first complex root of fifth root of negative 1 is this one right here. I'm going to write it as x1, and which is just e to the I 36 degree, 180 divided by 5. So this is 36 degree. Now, each complex fifth root, they are equal angle measure apart with 5 point on the circle. So that means next one is 36 degree. So next root is, fifth root of 1 is 1, so I don't have to, in fact, do that again. But it's equal angle apart. And now, so I do it 600 divided by 5. So that means that they are 72 degree apart. So 72 degree plus 36. So next one is 36 degree plus 72. And 72 is 360 divided by 5 because they are equal angle measure apart on the circle. So that's why I'm adding 72 degrees. So that's e to the I 108 degree. So 108 degree is somewhere here. And so next the complex root x2 is over here. So x2 is a unit circle, sitting on unit circle with 108 degrees. So that one is e to the I 180 degree. So 108 degree, e to the I 108 degree. Now next one is x to the third. So fifth root is e to the I is still 1, 108 plus 72. Of course, that's 180 degrees. So that means the next point, which means the complex number, negative 1 itself, is its root. (180°). So as you know, this point right here is e to the I 180 degree. And that's nothing but negative 1. So negative 1 to the 5 is a negative 1. So that's why negative 1 itself is a fifth root of itself. So negative 1 is a third fifth root of negative 1 because negative 1 to the 5 is negative 1. And now 180 plus the next one is e to the I 180 plus 72. 180 plus 72, which is 252. So next one right here is somewhere here. And this point right here is e to the I 252 degree. 180 plus the 72 degree, 252 degree. So they're equal measure angle apart. And this equal measure is 72 degree. And the next one is x to the 5, the finally fifth root of -1, e to the I, 252 plus 72, 324 degree, 324 degree, and which is somewhere here. And this is x to the 5, e to the I, 324 degree. And that's x to the 4. And x to the 3 is a -1 because -1 itself is a fifth root of -1. Now, of course, you're going to convert all this to rectangular form by putting in the calculator. And so this first one right here is cosine 36, I is 1, so I sine 36 degree. And put it in the calculator, give me a rough value. And this one is cosine 108 degree plus I sine 108 degree. And put in the calculator, we know this one. And cosine 252 degree plus I sine 252 degree. And this one is cosine 324 degree, and I sine 324 degree. And so put this in the calculator and get a decimal measure in rectangular form, x plus yi approximation. So I entered it all in a calculator and got the approximation, x plus yi. So this one is second quadrant, that's why you have x negative, say x negative and a positive. This is third quadrant, so x and y are both negative. It's fourth quadrant, x positive, y negative.